you, Alistair, for the introduction. Hello, everybody, and happy to join today's WoodSolutions webinar and to help provide some educational resources about mass timber, which goes towards TimberLab's mission to expedite the mainstream adoption of mass timber in the U.S. and why not the world, right? So without further ado, I'll go ahead and get my screen up here so we can start presenting. So today I'm going to share with you about the Portland International Airport project, which is a 9-acre mass timber roof, 400,000 square feet approximately. And it just opened with its phase one. Some of you, if you visited Portland the last month or so, you might have had the opportunity to walk through the airport. I just flew out last week for my first time, so got to experience it as a passenger, which was pretty cool. So a little bit about TimberLab and what we do. We're a holistic mass timber solutions provider. We do timber engineering, digital construction, strategic procurement, manufacturing, fabrication, factory installation of hardware, and the eventual timber installation on site. We're an affiliated company of Swinnerton Builders, and our specific function is mass timber as TimberLab. I usually like to start this presentation about the airport as a quote that I got from one of our forestry consultants we worked with on the project, and it's that wood should not be feared for its potential to harm forests. It should be embraced for its potential to leave a beautiful human footprint, one that reshapes our understanding of and relationship to land. And just thinking about that through the pursuit of this project really helped me put in the extra energy and effort it took to not only build a complicated mass timber roof, but figure out how to source it in the way that the client, the Portland International Airport, had the goal to source this wood. And we'll talk a little bit about that in the presentation. I'd like to start the presentation with a video, and
Design it so it feels like
gives you a kind of a feeling of what this project is.
How do you take one of the most loved airports in the country and make it even better, even more Pacific Northwest?
Design it so it feels like the forest.
You start with lumber from sustainably managed forests in Oregon and Washington.
You source from tribal lands across the region, including community forests and small landowners.
Making sure to be able to trace the lumber back to its origins from forest to frame.
We come up with a way to make these big, beautiful beams.
You hire thousands of skilled tradespeople to build a 9-acre roof right on the airfield. Together, we build something we hope you'll be proud of, a true testament to the spirit and people of the Pacific Northwest. We can't wait for you to see it.
This project's now open, so you'd be able to come experience it. A little bit about this project. It took a team of many. There's some stats out there that something about 30,000 people worked on the airport expansion project altogether. That was more than just the roof. It was a whole terminal core revamp at the airport. But specifically as it relates to the roof, the partners on there were the owner, which is the Port of Portland, the architect, which is ZGF, the structural engineer, which was KPFF. The general contractor for the project was a joint venture between Hoffman and Skanska. And as the mass timber trade partner, it started out as Swinnerton, and that's when we were Swinnerton Mass Timber. And during the project, we officially became TimberLab. And in conjunction with the steel trade partner on the project, which was WWAFCO. So that was the real partnership of people working together to make this roof a reality. Some highlights about the roof are its size, of course, 392,000 gross square feet. The large glulam single span beams of 80 feet long, MPP roof diaphragm that's 2 inches thick, glulam, MPP, and timber frame skylights. MPP parapets, and curbs. So there's a lot of different kinds of mass timber elements within the roof. Some unique highlights about those large beams is that, you know, as a single span member, 80 feet long, it's not only the length, it's the arch. The highest arch inside those beams was 16 feet tall. Our deepest beam was 9'3" deep and 80 feet long. And we also had to put 6-foot long reinforcing screws in some of the beam ends, which we'll share a little bit about later on in the presentation. There were over 1.5 million plus structural fasteners in the project that were installed by a maximum of 35 craft that we had on our site. So a handful of people installing millions of, or over 1 million screws, and 10,000 plus hours of mass timber detailing. The project started with manufacturing in 2020, but we started on the project back in 2019 as the mass timber trade partner, helping to get through the design development with the design team and to do a lot of mock-up testing and evaluating the details for the project to make sure this roof can be what it is today. So today I'm going to talk about design, engineering, detailing, sourcing, manufacturing, and assembly. And I'm going to focus a little bit more in depth in the detailing and manufacturing sections. That's a big part of what TimberLab does, and a lot of what was the magic behind how we made this roof come alive. To give everyone an idea of what this project is, it's an expansion of an existing terminal core, which was about half the size it is today. This is a view of the terminal core, a rendering of what's the finished product. We just finished phase 1, which opened everything except this little area over here and this little area here. Those will open next year. So those are currently under construction now, but the rest of this main hall and this pre-security area moving to security on either side is now open. For context, this is the size of the roof. It's multiple football fields or multiple city blocks. Here's some shots of the roof as it was nearing the end of the phase 1 construction phase. Some interior shots as we were closing up the interior roof after it moved over to the airport terminal side. And to talk a little bit about the design, which was designed by ZGF Architects, it really started from a place of how does the airport and the construction team keep this airport operational 100% of the time during construction. It was the port's intent to not affect the operations in any way during this construction. So that meant that you couldn't stick build a roof over the existing building because you'd have a giant crane up there all the time and that would impact flights. And so that's where the idea of creating modules that would slide into place one by one to not disrupt traffic, and that could be done in the middle of the night when planes are not being taken off. What this new roof was actually a new separate structure from the rest of the existing building. The existing building was going to be demoed here. They're going to maintain ticketing, maintain baggage claim and the baggage systems and the MEP system. So all this was getting maintained while also getting upgraded with the new expansion. And this was going to get torn down, a new roof getting moved in, and then a new whole terminal core being built above it. So it's quite a complex project to take on, and it took a lot of meetings and detailing and planning to figure out how to do it. And we played the mass timber part of this building. What the building was prior and after this roof, this roof was made of many different expansions over many decades and had over 1,000 columns inside of it. Today, the roof sits on only 34 columns. So you have 9 acres sitting on only 34 columns, if you can imagine that. This was the initial concept that the architect had created on developing infill cassettes that would slide in on rails. And they started with these smaller cassettes that would slide in by piece, but as they started to bring in the moving company that would move these cassettes, they realized they could make much larger cassettes, and we'll get into detail about that later. The evolution of the beam and how it connects to the girder system, it started with a series of details around how to get the beams to slide in and out of rails, because this roof was built off-site and then to be broken up into larger module cassettes and then brought back together at its final destination. So they had to find a way to build the roof, break it apart, and bring it back together. And so this detail became critically important. And eventually ending up on a detail that had connections that would allow the beams to be bolted off of the girders and transported over as large cassettes and then bolted back onto the girders. And we'll show what that looked like. The intent was to create these kit of parts that can be transported on these large module movers called SPMTs, self-propelled modular transports. And the roof was broken down into 19 different cassettes that would be moved over to the airport. And you'll see how they're numbered there, and you'll see how they're numbered in the airfield where we built them. Those cassette sizes were intended to work with the design and define the spaces within. And that was the marrying between the design and the structural system. And the geometries in the roof were really meant to represent natural organic shapes and reflect that of the Pacific Northwest. And this here was meant to look like a basket weave with the lattice coming together at a unique oval shape. On the engineering side, we did a lot of testing at the front end of the project to develop what could be a simple, repeatable connection type. And the engineering for the cassettes would sit on those 34 columns I mentioned, and those columns secured the roof to be seismically isolated from the rest of the building, while at the top of those columns, there's a seismic isolation bearing where the roof can move in up to 22 inches in any direction in isolation of the rest of the building. So it's a pretty unique structural detail that KPF created there. On the engineering side, it was all in a pursuit of how do we make this building as a prefabricated kit of parts that would be built out on the airfield and then broken apart into modules so that it became then modular and then brought back together. And that started with planning out the airfield side where these would be built and creating spaces large enough to build them. So we built the main terminal core on one pad, and then these other pads created the post-security areas that were on the sides of the main core. And the concrete in which it was set on was all built without rebar in it, so that concrete can get recycled and put back into the airport somewhere else later on. And the idea behind doing this was not only to not disrupt operations at the airport, but to minimize the risk of safety incidents, to bring a roof down from what's at its height today of 60+ feet in some areas inside the terminal with a lot of obstacles to get around. This roof was built at 13 feet off the ground out on the prefab yard. So it made it really easy to access for the craft and made it a much safer condition to work in. So it was like one of the most ideal conditions to work in for craft, not only because it's low, but also because once we got the roof on and we were working on the underside, you're out of the rain for the season. And it was actually a pretty nice place to work at. So this is how the modules were broken up inside the prefab yard and how they moved over to the site later that I showed. And you can see the beams sitting on site getting staged to put in place between the girders. These are the mega cassette and drawer cassette, the two different types of cassettes that comprise this roof. The mega cassette is the one in which the beams rode with the girders they were attached to. And the drawer cassette was one that slid out of the girders and rode on a temporary girder with just the beams and the roof diaphragm system. What that drawer cassette looked like is quite unique because you're essentially taking all the beams out of the girder temporarily and then putting it back into the girder, just like a drawer, just sliding right out and it's going to get slid right back in. Quite unique. And once these cassettes were broken apart, slid out, lifted up, they are then transported over to the airport terminal side where they would get erected into place. And this happened in the middle of the night to not disrupt airport operations because there's no planes taking off between midnight and approximately 4 to 5 a.m. For those who might be wondering, the speed at which these move is about the walking pace of a human. So you can walk alongside this as it was moving. This is an idea of what it looked like when it kind of got over to the terminal core and how it slid into place. There's longer videos of this on YouTube for those who want to see the full iterations of how this moved into place. And this is what it looked like up close and behind it as we were walking behind it over to the terminal core when it was being moved. Connections also took a lot of engineering testing and samples that we created and worked with universities to develop the right type of solution for this project, something that was simple and repeatable. These ended up really just being steel plates that, you know, served as tension and moment connections, but they're just simple SDS screws in these plates. A lot of screws though, there's 108 screws in each of these plates. So if you can count both sides of that, that's over 600 screws in one end of the beam. So a lot of screws to put into these large beams. And this beam here might look small here, but this is almost 7 feet deep at the end of this beam. So a little over 2 meters. Back to the drawer cassette and mega cassette and how that connection was created on the mega cassette. It's a welded connection that doesn't come apart from the girders, and for the drawer, it's a bolted connection that would allow our teams to unbolt the beams from the girder, working with the steel contractor, and to eventually re-bolt them back in after they are moved into place. One of my favorite parts about this project was the challenge of the large, long span, high arched beams that were originally designed as multiple pieces that would be married together with large spliced connections. So these connections were meant to be inside of the beam. So you would have had to cut out the inside of the beam to get those connections in and then screw hundreds of screws in to bring that together. And just the idea of bringing those pieces together perfectly, because these beams served as the foundation for the diaphragm, which was made up of over 1,000 MPP pieces that were all uniquely cut that had to fit in like a puzzle to a tight tolerance. This beam had to be perfect. And in order to do that perfectly, we thought we could achieve that if we did it as a single span beam. And that's when I set out to work with the manufacturer to establish a way to manufacture these things repeatably and as one piece so that we can get a tighter tolerance of the shape and also make the installation safer and easier for our teams to get it into place. There was a lot of risk I saw in this splice connection, so this was one of the biggest challenges of the project to achieve that. And the airport got behind it and we were able to get the support from them to do some testing. We made a mock-up beam here and that beam got installed in the main project. So it actually passed the mock-up. And so it was a successful investment in the tests. This is the 6-foot screws that we had to put in the ends of many of the beams. We had about 350 of these large screws to put in the beams. And this was the first one that we tested out putting in with our craft team. Because no one had ever installed a reinforcing rod fully threaded that's 5/8 of an inch thick and 6 feet long. We never installed anything that long before, and so we wanted to test it out before we knew we could commit to this kind of detail in doing this right. And you can see it's hitting a knot right now. If you can hear that noise, they're hitting a knot inside the beam. And he's going to be screwing this screw in for over 2 minutes long. And it just takes a tremendous amount of force and balance to get this thing to go in straight. On the detailing side, this is where we really made this project become an easy assembly. And that's really the goal of mass timber. You put your energy in on the front end to detail it right, detail it smart, so that you can serve your craft teams with enough information and the right pieces so that all they have to do is safely assemble different assemblies that come together as one. And what that meant was developing an LOD plan from LOD 200 through 450 that allowed us to see every aspect of this roof and understand exactly how it's all going to come together, how it's all going to come apart, so that everyone can confidently approach this project. And with that confidence, you find that you can turn a lot of difficult things into easier situations. Can let this just play a little bit and let you see how the detailing of the roof came together on some of these complex assemblies. These were the largest skylights on the roof that had a lot of intricate different pieces coming together, different fasteners, different wood materials, had MPP in there, had dimensional wood, and had glulams in there. These are the lattice down below and how they got fixed to the roof. When we worked with our detailing team on this at CAD Makers and started to develop these videos, this is when it really turned the light on for everybody, because it's really hard to visualize something like this on a 2D paper or just looking through a conceptual model. When you can see something 100% of what it's going to be, it makes it easier to envision not only how to construct it, but how to prefabricate it, how to deliver it, and make it an overall successful delivery. These are some shots of the digital twin compared to the reality. Many people asked how we were going to make this circle perfect, how we were going to cut it on site to make a nice circle, but this is all prefabrication. There was no cutting of this circle on site. And so if you plan right, you can get amazing things to happen. This is a breakdown of the assembly of the roof. It's steel girders every 100 feet on center with 80-foot glulam beams spanning between them. Skylights throughout the roof of different shapes and sizes. MPP roof diaphragm. There's 2-inch MPP panels throughout the roof, over 1,200 panels. An MPP parapet around the entire roof system, and that parapet was a unique feature to bring into the roof, along with MPP curbs for all the skylights. So rather than doing a built-up framed curb or parapet system, these are solid mass timber systems that just got dropped right into place, making the installation quick and smooth. Detailing on the glulam really began with breaking down all the different glulam shapes on the project, developing our manufacturing billet drawings, and developing our fabrication and installation drawings off of that, and how all of the cutting would happen and all the reinforcing and connections. Detailing of the MPP was also a very unique feature to do. We'd never done an MPP roof that bent it into complex shapes. If you can see here, this part of the roof was one of the most complex pieces to bend, and that's why it's the smallest piece, because it had to get bent in 4 different directions. It's going down there, it's going up there, it's going down there, and it's going down there. And so you have this convex concave shape happening all in one piece. And so understanding how that material reacts when you do that was a big part of the challenge. MPP, for those of you who don't know, is actually certified as CLT. It's really cross-laminated timber. It's cross-laminated veneers. And so that's a unique thing about MPP. It's manufactured in Oregon by Freres. And while we were learning about this product, we did a series of mock-ups to understand how it works when you put it under different stresses of bending it, especially as a 2-inch thick product. We would get it in sheets as large as 11.5 feet wide by 40 feet long, and as small as about 10 foot by 10 foot. And what we learned was, you know, if you bend it in certain ways at certain sizes, you get more cracking. We also learned how the material grows and shrinks. Here, this corner shrank in, and so we missed the ledger here. So that was a fail. Like we failed right there on that mock-up, and it's really should have landed perfectly down the middle of this, similar to this one. This one, we're getting close here, and eventually we got it real close, and we're able to dial it in and learn how to get the right shape cut to fit perfectly onto the 6 3/4 wide glulam that was every 10 feet on center down that roof. And eventually ended with a quarter shape of the most complex part of the roof that we did the mock-up on. And we did 5 different mock-ups on it until we, you know, realized how we could do this. But we still didn't get to 100% success before we started installing the roof. We just had the information we learned on what we failed on here, and we were able to take those last tidbits to the roof, and working with our detailing partner, we were able to assess that out and install it successfully on the first go on the roof. And what that meant was breaking down the roof into the right panel shapes based on the bending stresses that it was going to realize. And that's why you see on these longer, straighter runs, you have some bigger pieces. And as it starts to concave and convex down the bottom of that dome, these pieces start to get smaller. And so it's really a planning effort with our install team and our detailing team and the manufacturer on how best to size each piece for each part of the roof. Not only how to size it, but how to cut it. You would think that the manufacturer manufactures these typically as square rectangular pieces, and that would be fine if it was a flat roof. But given the roof had a lot of domes in it and vaults, the shape actually ended up requiring the billets to be slightly cut askew, almost like a slight parallelogram with some curved edges, in order to see when you bend it, you wouldn't get that shrinking, or you would be able to align it perfectly on the glue lams, or there was a tight tolerance on them. And what that meant was putting it into a program that would allow them to be bent into 3D, brought back out to 2D, and bent into 3D again to understand how they needed to be manufactured and cut in 2D, so that when they got bent in 3D on site, they would fit the precise shape that they needed to fit. Every piece was unique to its puzzle spot, so it wasn't like sending out a pile of this material in squares and putting it in place and cutting it here and there. No, it was, you need to find how to cut that piece precisely how it needs to be cut at the manufacturing level, so that when it comes on site, it fits precisely into its puzzle spot. And that's exactly what happened. And this was a shot of how that material came together on the roof. And not only fitting it into its spot, but we were given the challenge from the design team that they wanted all the joints to be parallel with the girders. And so trying to take a material you're bending like a sphere, like a piece of paper over a basketball, and making it so it doesn't crinkle or shrink or grow and fit in a perfect straight line was what kept us up at night about the early phases of planning on this project. This is the detailing of the skylight and how we got that together. And it really started with breaking it down into all of its components and developing assembly guidelines that our install team could scan with their phone or iPad with the QR code, and it would bring up videos and instructions on how to install that assembly piece by piece, step by step. The detailing of the lattice was very unique because we had over 30,000 pieces of lattice, 35,000 pieces of lattice, and these aren't just straight sticks. With a compounding arch that grows and shrinks, you have lattice that land every 1 foot on center along that arch. And at every point along that arch, it's a different bird's mouth cut at the end of that lattice. So modeling all those different cuts so that we can program it in the CNC and have these pieces manufactured and fabricated in the order in which they're to be installed was another big challenge of the project, and the detailing is what really helped get us through that. Because there were so many lattice and developing that program to cut the bird's mouth on it, it took over it took about 13 servers to process that. And so they tried it during the day and it crashed their whole office. And they learned that they had to do this overnight, which was pretty fun fact about the project. And what you see here is what we learned about the lattice that was unique. When the design team gave us a set of drawings, we saw a typical detail for the connection of the lattice, and knowing that this roof has a graduating arch, that typical detail really needed to be assessed. Is this really typical, or is it actually a unique detail at every connection along the entire slope of that roof? And what we quickly learned was that you take the pieces and, oh, trying to get it up here. I'm sorry about that. Start it over. Can't fast forward it. What we quickly learned was that the pieces were not typical, and by bringing this virtual video back to the design team, everyone was pretty wowed by the understanding it took to actually build this roof, and that every piece had to be individually assessed and evaluated for exactly what degree to bend the steel and what sizes to make the screws so that it all fit together structurally and aesthetically the way it was intended to. And so that meant modeling every screw, every piece, and understanding how that was going to come together. And so it worked fine here on this piece, as you can see how it comes together. And this is how the lattice would get installed. And this is the video that helped our installers understand how this bracket would come together on this, on the glulam beams. And it'll shortly go up to the roof here, and you'll see how we learned about the part where, you know, the detailing says more than 1,000 words, and it made us successful in finding the errors before they could happen in real life. I'll just let this play out for a minute here. It's almost over. And even little aesthetic things like this, we ended up showing this to the architect of, you want screw heads being, because the detail said 90 true to the earth, so that means straight down. But that then you'd have a head exposed like that, and that could affect the structure. So we brought that back as a question. There's also a hole right here that got created by this gap, and so we recommended putting a shim in there. And just bringing this information back to the client and the design team was really what helped answer and resolve a lot of issues during the design phase rather than during the construction phase. And this is really where we saw some of the major problems with that typical detail. That's the typical detail applied in this condition. You can see that you don't have bearing of that connection. So with the lattice, we broke down the roof into a system of cassettes and bays in which the lattice can be identified uniquely and installed in order. And we labeled each piece so that our install teams knew exactly which piece was where and how it corresponded back to the master puzzle drawing. This is a picture of the lattice under construction. And you can see some of the complexity of how to get this ellipse perfect around that shape. That took a lot of back and forth modeling with the design team and the detailing team to get that just right, the way the architect intended it to be. And so really the things we learned about the DFMA process is that it's teamwork and it takes constant improvement to get the QC process right. It requires scheduling and planning to ensure you're going to have a project that flows, and it's a whole team approach in order to make this successful. It's both internal and external partners that really make this happen. There's no I in any of these approaches. On the sourcing side, that's where it wasn't just building a complex roof. It was the airport saying we want to invest our money in local economies into forests that do a good job with managing their forests sustainably. And so that's when we set out to work with the design team and forestry consultants on how to best source for this project, not only from the places they wanted to source, but from places that can also meet the timeline of the project, of the manufacturing and the fabrication, because there's a whole queue of how that had to happen. So there's a lot of communication and a lot of hard work with all the interdisciplinary partners that were on the project. In different ways that we sourced it were from directly from forest to frame, from mills that could segregate, and from mills that can do batch segregation, or something, or mills that were vertically integrated where they own the forest, they cut the trees, they mill the wood, and then they can send that wood directly to the manufacturing to manufacture specifically that wood. So it was quite a unique way to do all this sourcing, and we learned about all the caretakers that we worked with, and the airport honors them throughout the airport, which is pretty cool. The manufacturing part of the project's one of the most exciting for me, in learning about glulam and how to manufacture really large complex members like we did on this project. This is the 16-foot member I mentioned. It's 80 feet long with 7-foot, 4-inch deep members at the end, and it's 4 foot deep in the middle. And so this beam was manufactured as a main center beam, and then it had a built-up section on the top and a built-up section on the bottom that got manufactured on it as a secondary process. And then there was a 9'3" deep beam that's 80 feet long, which was huge for a glulam. And what that process entailed was developing the drawings and the plans to get there, but going a step further and actually making laser cut guided sheet metal shapes to help set up the jig in which these were going to be pressed in to ensure we're going to get that exact shape. And following through on those add-on sections, how those sections got cut, then stained, and then this was the mock-up of that install. Taking that process and breaking it down to a schedule and a flow, the manufacturing is not as fast as the install. And so we needed to start manufacturing about 4 months prior to install so that we can start manufacturing the members that needed to be manufactured. This is the list of the unique members and the month in which they're manufactured and the quantity for each month of that specific unique beam that needed to be manufactured. And that corresponded to a delivery schedule and what got delivered. But it also not got corresponded to delivery schedule. It got corresponded to the manufacturer's efficiency and what made sense for them to manufacture as batches And what that meant was if you're going to manufacture in batches, you need to create a storage plan. And working with the manufacturer to find the space within their facility to dedicate to this project. And so working with our manufacturer Zippo on this project and going to them to say, hey, look, we need to take over like half your facility for the manufacturing, and then we need to take over half your yard for storage. That's not an easy thing to do, especially with a company you're working with for the first time and on a project that's the biggest project for both of you. And so it took a lot of trust building and communication to develop that plan to make sure this thing was going to be a success, and developing, a process. It started with, how are we going to do this? We've got these giant 80-foot curved beams. How are we going to move these through our facility on a production type of mentality or tempo? And so it just started with sketching it out, and this was the later sketch of what started with some hand sketches and the idea of doing this. And we ended up bringing not only the manufacturing, but the reinforcing of those large screws and the coatings of those beams all within this facility to make one production line, rather than trying to send these to different places to get this future value add on them. And what this looked like in pictures started with the manufacturing process here at one. The lamellas would get dropped into the press. They'd get pressed. Then they'd make their way over to the planer. They'd get planed. What's unique about this is these beams were long and curved. So Zippo had to set the planer on the outside of the building and actually send the beams outside through the sidewall curved. So they got multiple pieces of equipment grabbing it to try to run it through on a curved radius, and then adding the add-on sections for that bottom and top of those end beams, staining it, putting reinforcing screws in it, and then sending them out the door. Then how do we ensure they were making these beams precisely to the shape they needed to be made to, because they needed to be built with a tight tolerance? We took our scanner out there, and this point cloud scanner can scan within a 64th of an inch. And so we would go out there at the end of each shape being manufactured and go and scan the beam to make sure that it was going to be compliant with the construction process. And there were 272 of these beams that had to be made, and only 5 didn't meet the shape requirement initially. So we had to make 5 beams twice on this project. And to give you an idea of what that looked like, we scanned each beam, brought it back into the model, the point cloud shape, and we found that some of them were up to 5 inches off, and those quickly got fixed. But for the most part, everything was super tight tolerance. Zippo did a great job in manufacturing these things to an 1/8, a 1/4 inch, in very rare cases, a 1/2 inch, and it would only be at a small part of the beam where they get manufactured off a little bit. But those were all good enough to work with to get the MPP on the roof set precisely where it needed to be, and the corresponding lattice below. On the assembly side, this was where it should be downhill if you did the planning and the detailing right on a mass timber project. And this is really the beauty of the mass timber industry or world. How we want to look at is, this is the value of mass timber if you get it right. And it's turning construction on its head. It's taking what's traditionally been an industry that has a design that gets worked out during construction with a series of RFIs and questions, and most likely delays and cost increases because of the unknown that you don't have in a design that way. But when you design a mass timber building, you have to figure out every inch or even fractions of the inches of a building prior to any manufacturing starts. And that, if done, can make the assembly process a breeze. That's when the project team can sit back and watch what's really artwork. It's the assembly of this beautiful structure just come together. And this is what it looked like for our craft team to install the large beams in the girders. And it was our woodcraft working alongside our steelcraft partners. And they would go up in scissor lifts together. It was a unique thing to see because you usually don't see carpenters working with steel erectors nicely. And this project really defied that. We had a great team of both carpenters and steel erectors working together as one. All right, on the MPP side, the install was a little unique because we had to bend these things. And how do you bend these things up in the air with, you know, them being lifted into place with a crane? It really took a handful of courageous men and women to go stand out there and bend them to the roof by standing on them and fastening them one by one along those glulams. But not only just going out there and doing that, but thinking about where you start and how you progress through that fastening. So as it starts to adhere to that shape, it doesn't grow or shrink into the wrong direction. It fits precisely into that spot where it's supposed to fit. So there was a lot of planning and intentional thinking that went in around the installation and the sequence of how it got installed with each screw. And this is that circle that I so love on the project that came out perfect. We were all pretty worried about it at first, and this really proved the testament of DFMA process and prefabrication altogether. That circle from another shot. And what the install guides really were for this project, there were a set of instructions like you would have for assembling a bike or assembling a piece of furniture at your house. And it really made that process for the craft team to bring this thing to life a lot easier. And so if you think about your craft and how to best serve them so that they can do what they do best, is assemble things and build things, then they will be successful. Here's that complex skylight and how that came together and what they would get when they would scan the install guide. It'd show them, you know, where they start and what pieces are there and how this thing would get erected. And so with that information, you really make the installer confident and capable to install this thing safely and correctly. There's the MPP going on. And each material is a different color. So you can correspond that back to the install guides, which had each piece of material in a different color and labeled with its quantities and sizes. These are the MPP curves that went up around the skylight that just got put together with straps and just bolted or screwed right down to the roof. So a pretty simple assembly. These curbs went in a matter of days. We're almost there. Just want to let this one play out. It's pretty cool to see if you've never seen this video. Got threaded rods going through each of these assemblies that have nuts on them that screw in different directions. So thinking about how those rods need to be manufactured and which nuts go where was also an important piece of information that needed to get to the installers. These are the curved lattice on the underside that were actually cut out of MPP. And that's why they're the same color as the roof. It's the same material. And so that's how we made that skylight a reality, and this is the install team bringing that together. Here's a shot of that skylight and how big it is. And what those curbs look like that went around the roof, that went around the skylight. Lattice assembly of that skylight also. The MPP. This MPP was cut out into unique arches. And that's the Portland International Airport project that I've had the pleasure of working on for the last 5 years, and we should be finished next year. So thank you for taking the time to learn about this project and our process, and hope you got something useful out of it. Thank you.
Thanks for that, Jared. That was absolutely amazing. What can I say? I think in my sort of 40 years as an engineer here, I don't think I've seen a project so spectacular. So well done. I mean, not just the amazing engineering and the manufacturing, and but I mean that, you know, those digital twin models and things that you were producing are just absolutely stunning. So so absolutely well done. We've had some, we've got quite a lot of questions here, so I'm not sure how many we'll actually be able to get through in the time we've got left, but we'll certainly do our best. But couple of questions earlier on around design life. What's the design life of the building in terms of its primary and secondary structures? What we're working on there?
So the design life of the building is intended to be there for the next century or more. And the way it's built, given that it was a modular building, it could be thought through to take that apart in the future generations. But these things, if properly maintained, I think it could last more than a century, no problem. You see wood buildings that are more than a century old in the United States and Europe, and even in Australia. I would imagine that if properly maintained, that wood and that system can last a really long time.
Absolutely. And just on that, you mentioned a second ago about the way it goes together. What was the thought around design for deconstruction? Certainly a sort of big thing out there with the design community at the moment. Is that the thought in the future? It can just all be sort of unscrewed and bits reused?
I believe that's a consideration, but the main thought was really about how to get this thing in place without disrupting operations, and having that ability of it going together that way makes it much easier to come apart that way if need be in the future. So I'd say that we'll let the second or third generation from now think about that when they face that problem, but it would be much easier to take this roof apart than it would a piece by piece built roof.
Yeah. Actually, I must admit, I was thinking at the time when I was watching the guys manually install those screws, and people did ask the same question. So all of those big, long 6-foot screws that you were talking about, they were all manually installed. You couldn't automate that in any way?
No, all those screws were manually installed, and given that they're 6 feet long, the longest drill bit we could find with an extender on it was a little over 4 feet. So we would pre-drill the whole 4 feet, and mind it that the beam is only 6 3/4 wide. So we'd put that beam on its side and align that drill bit to try to go as straight as possible into that beam. And then the last 2 feet that couldn't be pre-drilled, we would just pray that reinforcing rod would continue straight and not pop out the side.
Yeah.
And we did experience a handful that they popped out the side, and what we had to do is go back and work with the structural engineer, and the solution was pretty much cut it out where it popped out, patch that up, and put another screw in next to that and pray that that one doesn't pop out. And we never actually had 2 pop out at the same spot. So we would experience once and get it right next to it, but we had that probably happen a handful of times out of 350 screws that we installed. So it was a pretty low percentage of failure on that one.
Absolutely amazing. There's been a couple of questions around durability. What was the durability of the species of the timber used, and what did what was the consideration around durability?
The species is Douglas Fir, which is probably the best timber you can use for glue laminated beams. It's some of the strongest timber in the world. It's a soft wood, so it's also flexible. But given that these beams were so deep, and that was one of the things we were worried about when we were manufacturing these into a curved jig, we thought that they might, when you press it and let it cure in that shape, that when you release the pressure off that jig, we were worried that that piece might deflect a little bit and come out. But because they were so deep, that piece didn't move or budge an inch when it came out of the press. So we learned that when you have such a deep member, you can really get a precise shape that's not going to budge when it comes out of the manufacturing jig.
Mm-hmm. And were there any, what was the sort of consideration around fire design? There was a couple of questions there on that. There's special requirements there in terms of so much timber being used?
Yeah, it's actually a unique thing that this is a non-fire rated roof, and the design team was able to achieve that because of the height of the roof. They were able to demonstrate that a fire anywhere in the building would not be able to reach the height of that roof and cause fire to it. And so they worked with the JHA, the jurisdiction having authority in Portland, to work through that design to prove to them that there wasn't a fire risk of that roof. But mass timber in general is a pretty resilient system when it comes to fire, and wood itself will char at about 1 inch an hour. So it's kind of like throwing a big giant log on a fire, and you never see a log just spark up and totally get torched quickly. It takes a long time to burn that log, and that's what the big glulam beams are kind of like.
Yep. Thanks for that. Look, we're just on the hour, so we're going to have to sort of cut it short there, but an absolutely amazing project. So well done to you. It's been a big part of your life, obviously, but you must be so impressed. I've got to say, the thing that blew me away about it also was the cassettes and the prefabrication and the installation. I know in the length of your presentation today, you didn't get a lot of time to speak on that, but as you say, there's some quite good YouTube videos out there if people want to sort of see a bit more about that. But a really amazing project. So once again, thank you very much for joining us all the way from Portland to present that to us today. I just remind people that the webinars are all recorded, so this will be uploaded in the next couple of days. So if you'd like to go back and have another look or tell your colleagues about it, it's such an amazing presentation. You can certainly go back and relook at all of the webinars we've produced previously. Our next webinar will be held in the normal schedule of events on the first Tuesday of December. That'll be December the 3rd, and it's all around acoustic and vibration control of prefabricated timber floors. So we encourage you to join us for that one. So thanks again to everyone for joining us today for this WoodSolutions webinar, and thank you once again to Jared, just absolutely amazing, and I wish you all well.